the record. Okay, so I am sharing my window, right? You can see the slides. Okay, so well, this is week 2, end of week 2. I mean, we have been doing this course for 2 weeks now, and actually I consider every course, undergraduate or graduate, they actually start after 2 weeks. I mean, 2 weeks are a nice interval to get used to or to get prepared for a course, in my opinion. And I think we are ready. What we've done was previous week. Let me show you. We had a slide like this. So where is it? We had this slide, you remember? We've talked about a general architecture of a microprocessor. And in this general architecture, we have seen the general components of a microprocessor, which is the arithmetic logic unit, the program counter, the clock, some registers, and some instruction memory and type of memory. So you've seen that there are special registers and some memory or some arithmetic logic unit which can do operations. And we have, since you all know digital design, I mean, some of you are registered to the course with this course, I know that, but in digital design, most of you have seen what an adder is, what a counter is. But these are some circuits which were designed using those techniques, and you've connected them. And they formed up a general microprocessor architecture. Then, after seeing a general microprocessor architecture, we've switched to ARM. We talked about what is ARM, why is it important, why it is important. Then we've talked about embedded systems, and we've talked about we've got processors in every device in our lives. I mean, washing machines, your phones, whatever. And it's going to grow. I mean, in your shoes, you'll have them everywhere. And actually, being very complex or simple, there are various designs of microprocessors, and actually they are based on a similar architecture, which we are going to learn. That's the purpose of this course, to learn the general microprocessor architecture.
Hocam,
please.
Bölüyorum ama bir arkadaşımız derse girememiş.
Ama waiting room kapalı.
Yani bilmiyorum, beklediğini söyledi. Hatta şey yazıyor, host'un sizi hani izin vermesini bekliyor.
Allah Allah. Benim burada bekleyenler arasında kimse yok listemde. Admit desem öyle birisi yok.
Tamam hocam, ben söyleyeyim ona.
Acaba yanlış bir derse mi girdi?
Hocam bir de dersin sitesinde Zoom'un o ID şeyinde numaralarında sonunda 1 eksik.
Ondandır. Adam başka bir yerde bekliyor. Peki siz bu derse nasıl giriyorsunuz o zaman?
Zoom link yazısının üstüne tıklıyoruz biz.
Tamam.
O da öyle yapmış ama yine de
o zaman bir daha çıkıp bir daha girmesini rica edeceğim.
Tamam.
Böyle bir sorun varsa.
Tamam, ben söyleyeyim hocam. Teşekkürler.
Evet, ben de şeyi düzelttim. Çok teşekkür ederim. Bir bakayım arkadaşlar. Allah Allah ya, böyle oluyor işte böyle şeyler. Evet. Nasıl böyle bir halt yedik ya biz? İstesen beceremezsin yani şöyle bir şey. Yanlışlıkla oldu herhalde.
Hocam tamam. Ben size bir hafta önce mesaj atmıştım. Oradaki
bu konuyla alakalı mı?
Aynen.
Şimdi vallahi ya ben
de girememiştim kaçtı. Çünkü ilk hafta.
Spam oldu ya da benim gözümden kaçtı. Okey. Arkadaşınız girebildi mi?
Hocam bilmiyorum. Soruyorum şu an.
Çünkü yani waiting room kapalı. Yani waiting room yok. O yüzden gelen giriyor şu anda. Tıklayan giriyor.
Tamamdır.
Tamam. Okey. Ben devam edeyim. Bir sıkıntı olursa sen yine durdur. Tamam mı?
Tamam hocam. Teşekkürler.
Tamamdır. Okay. So we talked about why ARM. Because ARM is a complicated architecture. We're going to learn the basic architecture, but ARM is a complicated architecture. And then, while we were discussing the architecture, we have solved a problem in which we have considered some bits that connect the instruction memory to the other devices. We had bits here in the previous week slides. And those bits were machine codes, and they were the commands, the bit commands in bit language that we used to control the microprocessor components. And we said that this is a language. And this is the actual language we're going to learn. We called it assembly language. And we said that, and we have, after seeing this generic design, we have switched to the actual Cortex M4 microprocessor that we are going to use. And we said that we are going to use this design. Okay. And we said that, for example, the internal peripherals correspond to registers here. So we just understood this architecture. Then we made a brief introduction to different registers, because in the generic design, he had so few registers, and some registers we could write on. However, and this program counter, we said that these are like registers, but we have many other registers. We have talked about them, we have defined them. We didn't explicitly learn what they are for. We said that we are going to learn these, don't worry, but these are just some registers. And when you say a register, since this is a 32-bit system, it means this is a cell. We always gave the same example, the hotel room example. So these are hotel rooms. And in the front door of each room, we have these written, R0, R1. These are the hotel rooms. And we know that in each of these rooms, there are 32-bit information. There exists 32-bit information, and we can just read it, write it, change it, and therefore something. And we said that these were the scratch registers. These were used for müsvedde kağıdı, to do operations on. But these were special registers, as the name implies. They had a special purpose. What purpose? Well, I mean, you don't know what stack pointer is, we don't know what link register is, but you know what program counter is, because program counter is exactly the same as in this example. We'll have a set of codes which will be written in the memory. We'll call that part of the memory instruction memory. And the program counter will point to the address, because there will be different memory cells here, just like these cells. Sorry, just like these cells, bank of memories. This is full of cells. This one is also full of cells, this one. And each cell is sequential. Sequential means ard arda. One comes after another. And the program counter says, I'm pointing here now, so run this code. I'm pointing the next one now, so you run the other one. And the clock will make the program counter count. So with the clock, we do operations. That's why the clock speed of a microprocessor is important. Because if you can do high clock speed operations, we will be doing the operations faster. So that was the general idea, guys. And we also talked about some other special register, which was called program status register. We said that it has many specific bits.
Hocam bir şey sorabilir miyim?
Please.
Aklıma takıldı. Bu işlemcilerde hani bir hız var, bir de çekirdek var ya.
Hı hı.
Burada önemli olan hani çekirdek, düşük çekirdek yüksek hız mı? Yüksek çekirdek düşük hız mı?
Well, you're saying the number of cores, right? Number of çekirdek, yes. Okay, your friend is asking, we have the speed of the microprocessor and we have the number of cores. Actually, number of cores is the number of this architecture in a quad-core system which has 4 separate microprocessors. It is a bit different design. We are not going to see this in this course. We are not going to examine multiple core microprocessors. But in a multiple core microprocessor, with this basic design, you have 4 of them, for example, in a quad-core system. But they are all connected to the same memory. So they are using a memory in a shared manner, but they can work together. So which one is better? Well, both of them are good. Because if you're doing your operations fast because your clock is fast, that's good because you'll be doing your instructions fast. However, in some cases, you'll need to do some operations simultaneously, eş zamanlı. For example, in an operating system, while I'm speaking to you, there's the camera, and I'm using the mouse. They are simultaneous operations. And if you have many microprocessors, they do these operations simultaneously. And actually, it's a faster way of doing things. So a good question could be, well, most microprocessors are single core. So how come they do it? Well, this is a complicated question. This is related to some embedded system stuff and operating system stuff, so other courses. Actually, it does something called scheduling. Just it does one work and it does another work. It just switches between tasks. However, if you're, regarding your question, if you're doing complex operations, like an operating system, like a phone, like a smartphone, multiple cores are, is a must. It's a must. However, if you're doing something simple, like a washing machine, But if you need to do it fast, for example, a signal processing system, you are capturing data. For example, a graphics card, it's not a good example, capture card. You have a camera connected to your device and it's capturing the camera. You just need one microprocessor because you're reading the information, but it needs to be fast. So it depends on the application, the answer is. That's a good question. Okay, and we said that we are going to learn this. And we said that we're going to delve into assembly code and we'll have a love affair with assembly code because this course is all about the assembly code. And we said that assembly code is the machine code that the architecture understands. What we said about the machine code, assembly code was, it is specific to the machine. What I'm trying to say is, I've given the same example the previous week, you remember. Imagine you're using MATLAB. When you're using MATLAB, you just write codes. I mean, int a equals to 4, no, you don't say int is from C. A equals to 5, B equals to 4, C equals A plus B. Well, you did not just care about anything about the hardware. How many microprocessors do I have? What is the type of micro? Is it ARM or is it an Intel? You didn't care. It's a high-level system that takes care of everything. So you didn't care. That's why it's called a high-level language. But when we are doing assembly coding, we will be touching these registers. We will specifically say, okay, there is a hardware register there, which is called R0. Get the value inside R0 and write it to R1. So it is not like int A or A. A is a theoretical variable. You don't know where A is in the memory. But R0 is a hardware register on the card. You are touching it. You are saying just get this value and write that value from this part of the registers that to R5, for example. So assembly is all about touching the hardware. And that's why it's a low-level programming language. It is the lowest level that you can program. It is the lowest programming level that a human can program. So that's why you should learn it. If you want to become an embedded programmer as a human being, you should be able to touch it. Okay, that's what we are going to do in this course. Okay, so what does that mean? You remember the slides from the previous week. We had these machine codes, and I had this in the instruction memory. You remember this? Instruction memory. So when I had this line here, because of the connections, because this is 1, this hex nibble is 1, and 2 bits of that nibble were connected to the ALU, which made the ALU to do the subtraction operation. That's why this 1 here means subtraction. Which operands? Well, register 3 and 4 because of these nibbles, because this information goes 3 here. When 3 is connected to here, register 3 will be outputting data from this line. So all intertwined, interconnected lines will create the language for you. And actually, since we're human beings, you don't like speaking like 1, 3, 7, 4 kind of things. We just make them written in a language like text, like this sub 7, 3, 4, which means register 7 will be written with the value which you will calculate from subtracting register 4 from register 3. So this is the assembly language. This is the machine code. They are one-to-one. So for each machine code, you have a specific assembly language. As human beings, we are going to learn the assembly language. Kale, our interface, will transform it for us to the machine code, and the machine code will be run by the microprocessor. Okay? If you get into the details of the architecture, you can definitely understand what this assembly means as a machine code. For this simple architecture, we know. When I say add 6, 3, since add is 0, 0 for this ALU, I know that this is 0, 3, 4, 6. But in our architecture in ARM, I don't have to know this because this is not a computer architecture course. If it was so, we would be interested in that, but it is not. In this course, we are at this level, not lower. We'll be writing these kind of codes. And ARM has a specific assembly language. We are going to learn it. It is like this one. It looks like this one, but it is not. This is not an ARM assembly language syntax. It is just something we created. I found it on the internet. Somebody created for this simple architecture. But it will be looking like that. How will it look like? We said that there were 4 fields. 2 optional, 2 compulsory. You always have them. So the label, actually this is the address in the instruction memory. What does this mean? You don't know yet. You'll learn. opcode and operand. Opcode and operand, and it's very simple because opcode is subtraction. This guy tells the arithmetic logic unit what to do. And the operand is where to do the operation, which registers. Usually the ALU will do its operations on the registers, guys, usually, most of the time. And we'll see that. So it will be like, you'll write something here, add or multiply, register 1, 0, for example, move, which simply does this operation. You move this value, 150 decimal, because I don't have 0x here, this decimal value, it moves this decimal value, writes this decimal value over R0. Simple. And this was ARM assembly, guys. It's very simple. These are the comments. I mean, it makes you understand the code. It's written for you guys. But this is the label. It is the place of this code in the instruction memory. What does this mean? We'll slowly get there. So, okay, for fields, optional, used to find the position of the current instruction in the memory. You remember, each of these instructions were written in the instruction memory. And at each cell of the instruction memory, you have an address. For example, this is written to address 00. And this is written to address 01. So each line of machine code, which corresponds to a line, is written to an address here, right? So this designates that address, guys. But we are not going to write the memory address like 001 because an address in a memory is a hexadecimal number, binary number. But we'll be using labels. We'll say start. We'll say start. We'll say start, and we'll understand that code starting from that point will be written to a memory, part of an instruction memory, and we are pointing to that memory by saying start. Whenever you say start, it will be pointing to that part. How? You'll get there. So there was a very simple example of a code. So this was the label. It means that this line of code, this is a line of code. It will be written to the instruction memory, right? It will be written to a part of the instruction memory at an address. You don't know where it is. For example, this will be written to this address somewhere here, 00, for example. Since I've defined start and I've written this code, start is actually automatically this address 00. You don't know what start is. It's somewhere in the memory. The compiler, the system will know it. You don't have to know. You are saying that, hey, assembly, I'm going to write this code, and you are going to put this code in the instruction memory somewhere. I don't know where you're going to put it. I don't care. But you are going to start writing from somewhere, right? You are going to put the first line to somewhere in the instruction memory. Well, that starting address, let's name it start, okay? That's the beauty of it. Okay, why are we doing this? Maybe we are going to jump back to it. You remember, this guy is executing the program one by one. It's executing this one. Then the program counter moves this one, this one. So the clock is changing the program counter. But imagine there is another mechanism changing the program counter. I'm telling the program counter somewhere, its program counter is pointing to 03. It's just executing something. At some moment, I say, hey, program counter, go back to 00. It will be jumping to 00. So it will be like a jump in my program. Since I will not know these addresses, I will not know these labels. And actually, there will be an instruction. You don't have it here. It's like this here, BL. It's called jump, branch. B stands for branch. Branch means something like a jump. You're going to jump to a label. That's why this is also a label, guys. It's an operand, but it's also a label. So in this code, which is going down here, somewhere there's a label with this SSR in it. Okay, so I mean, complex things, I know, but you'll get used to it. Don't worry. Make microprocessors courses like this, guys. I introduce you a concept. You just understand it half. You say what's going on, but in time, it will sink in. So do not hesitate to ask any questions. So let's go over the code. Instruction LDR. You have no idea what it is. Because there is a data sheet of thousands of pages, it explains every instruction. And LDR is actually stands for load register, which means load a value to the register. Which value? It's called M. What is M? We'll get there. Similarly, load a value to R0. What is this value? Seed. We'll get there. STR, store register. I'm going to go over these instructions one by one, don't worry. Store, okay, I'm going to store a value to R0, but which value? From where I'm going to read it? Most probably I'm going to read it related to something R2, but there is a square parenthesis here. What does it mean? We'll get there. So everything you write is very important, guys. That's why the assembly syntax in a language is the grammatic rules in that language is very strict. You should be very careful with every inclination or sign you put here. These all have meanings, and we are going to learn them. And these comments, the fourth field, you are writing it for yourself. You have written a code and you want to read your code 1 week later. You just don't understand what you've done. So these comments will help you to understand it. I mean, assembly code is a bit complicated. That's why commenting in an assembly code is more important, much more important compared to commenting in a MATLAB code, because MATLAB code is more readable naturally. Okay, so guys, we have this code. Let's try to understand this code in more detail. For example, start. I've got this architecture. This is our architecture. I told you we have a memory in which all the instructions are written. And it is this part. It's the instruction memory. Instructions are written in this part of the memory. So I've got in the instruction memory some lines, some binary codes. They correspond to my lines of code. So it is like this line, LDR-R2, is coded such that it's a set of binary values. Just like this example. You remember? Since this hexadecimal, this binary code meant this, right? In our architecture, we have something similar. This LDR-R2, blah, blah, means something. You don't have to know this. In this course, you are not responsible for this mnemonic transition to these binaries. That's computer architecture. It's about the connection of the architecture. We don't care. We are going over this example to make you guys understand it. But we have this architecture, and there should be a corresponding binary machine code to this line of code. And actually, when I write this code and when I do my operations on this interface scale, I upload this code to my card. And it writes this code to the instruction memory, starting from an address. Which address, I don't know. For example, it is this address. The addresses have 32 bits, so it is 8 nibbles. 8 nibble, each nibble 4 bits, 32 bits. Be careful, this is an hexadecimal. So these are hexes. 1 hex digit is a nibble. A nibble is 4 bits. 8 hexadecimals, 32 bits. So each address in my system has 32-bit value. That's why this is a 32-bit system. We'll get there. So it started to write my code starting from this address. Since I said start here and started writing these codes, actually I have defined this address as start. Whenever I say start in my code, the microprocessor will understand that I am referring to this address, guys. Any questions about start label being an address in the instruction memory? Any questions? This is something important.
Hocam benim bir sorum var da bu hani biz dedik ki hep hafızalarla ilgileniyoruz falan. Şimdi bu biz diyelim ki bu kartı aldığımızda adresler otomatik olarak R0, R1, R2, R3, R4 olarak kodlanmış şekilde oluyor değil mi? Biz sadece bunları kullanabiliyoruz. Yani mesela atıyorum L55 diye bir adres yaratamıyoruz değil mi?
Exactly. Well, let me try to explain it because okay, that's a nice question. Let me answer it. But the question was confusing in the sense that there is memory and there is registers. They are different things. Yes, R0, R1, R2 are specific positions, and you have R12, but I don't have R20. Those are specific. You have only these. You cannot define it. So these are not like variables in MATLAB. You are right. In MATLAB, you say int Erdem. In MATLAB, you don't say int Erdem. You say Erdem equals to 3. And Erdem is a variable. It's a theoretical variable. It is 3. I can name anything. Rihanna equals to 4. I can't create anything. It's not the same here. The registers are here, and you have only these. And apart from registers, you also have the memory. Instruction memory and data memory, guys. And still, in that memory, we don't have names. We have addresses. So These are cells, some number of cells, many cells. These are just 13 cells here, very little number of cells. We only call these register 1, register 2, register 3, and we call these by their addresses. You cannot create any other thing. So whenever you use a memory, a space to write a variable, just like you said, it should be something specific in the hardware, either registers R0, R1, or an address. An answer to your question, I hope?
Yes.
Okay, wonderful. I'm glad. Okay, any questions about start being a label and actually pointing an address in the instruction memory? Good, very good. So guys, what I said was, I said LDR equals to M. Actually, LDR equals to M means M is a variable. And in my code, you'll see in time, I'm going to define variables, just like I do in MATLAB, like Rihanna equals 4. But whenever I define it, actually M will be pointing somewhere in the data memory. So these labels are pointers in the instruction memory. These definitions, M seed, are labels in the data memory. And I will have to define them somewhere up in the code. You don't see it, but they're already defined. So actually, I lied to you. We can define codes like Erdem equals 3, but there's a specific way of doing it. And whenever we do it, actually, we know in which part of the memory they are. So M is a part of the memory. So it is like, hey, LDR, get this value. So there's a value. It will be reading that value. So whenever I'm talking about a variable, it's either a register or a label pointing to the instruction memory or a variable pointing to the data memory. Okay? That's all I want you to get this from this slide. You don't have to understand what this code specifically does. I mean, there's the square, or we don't have the square here. There's an equal. We'll get there. So don't panic. Just bear with me, okay? Okay, guys. Let's start with the assembly instructions. And let's learn what these instructions are. After we go one by one on these instructions, these lines, I mean these lines of code, will make more sense to you guys. Load register. It loads a register with a 32-bit value, okay? Depending on how you use it. For example, this line, LDR R0 equals FFF, it puts this value to the R0 register. So as you can see, this is a value. I didn't read it from anywhere in my microprocessor. I defined it. I told the microprocessor, okay, there's a value, FFF, it's a number in base 16, hexadecimal. Write it to R0. It automatically does it. So I didn't read that value from somewhere. I've introduced that code in my, introduced that value, FFF, in my code. That's called actually immediate value. I'm immediately giving that value. Don't read it from somewhere. I'm telling you the value. It is directly telling the value. Okay, just my mouse is. But I can read the value from somewhere else as well. So actually, if you look at the architecture, let's talk about LDR in specific. When I'm loading a value from to R0, to R0, I'm loading a value to R0. I'm going to put a value inside R0. What are the possibilities? The first possibility is, just like we've learned now, I can immediately put a value. Put FFF there. The first probability, put that value there. The second probability, for example, I could be reading a value in another register. So get the value inside R4 and write it to R0. So the second probability is reading from another register. Since these guys are in this small box here, they are very close to each other. Or I could read it from the data memory here. Okay, read it from the memory. Well, you should think that, well, reading from a register and reading from the memory. What is the difference? I mean, this is a 32-bit cell. This is a 32-bit cell. I understand architecturally it is here and it is here. So what is the difference? I mean, architecturally they are different, and in assembly we'll have to do them in different ways. How come? I'll get there. So guys, when using this instruction LDR, when trying to write a value to a register, I have 3 different possibilities. Telling the value in the code, reading the value from another register, or reading the value from the memory. Actually, these 3 possibilities are called addressing modes. Okay, guys. So when you're telling the value, write this value there, you'll be immediately writing it. That's called immediate addressing. And immediate addressing, it's very simple. You use LDR, comma, R0, comma, equal sign, and the value. If the value is a dash and doesn't have 0x, it's a decimal. This is wrong, guys. This should be hexadecimal value. So because this is A, this cannot be a decimal. So I'm going to consider this A as 0, so it's 90. I'm putting 90 to that register. Okay, I think you've got this from the previous example as well. So this is immediate, and this is immediate as well. The other one is directly reading from another register. The second possibility, you remember? Reading from one of the other registers, one of these sister registers here. It is called direct addressing, direct addressing. Indexed addressing is actually reading it from the memory. Wow, reading it from the memory, you'll need these square brackets. Because when you're reading something from the memory, you have to tell the guy which address in the memory. Okay, I'm reading it from the memory, but memory is huge. Which address? You put the address here, but you cannot immediately put the address here. You cannot write the address here. The address should be in one of the registers. Actually, this is a bit complicated. It will take a couple of weeks for you to understand, most of you to understand this. Maybe some of you have already got it, but it's a bit complicated. We'll get there. So in these registers, there are values written. For example, in R2, there's a value written. Consider that in R2, I have this value written. This hexadecimal value. Assume in R2, I have this value written, 3001, blah, blah. Okay. If you have this line of code, it means that, hey, I'm going to write something to R1. The content of R1 will be changed. I'm going to write over whatever it says. Just forget it. I'm going to write something over it. Okay, what are you going to write? I have square brackets here, which means I'm going to read something from the data memory. Okay, which address in the data memory? I'm telling you. The address of the memory location that I want you to read the information from is written in R2. Go check R2. Okay, let me check R2. In R2, I had this value written, so just copy and paste it here in R2. Okay, so since I have square brackets here, I think that, this is a square bracket, this must be an address value. It is pointing to somewhere. So in R2, I have this value. So I'm going to go to this memory address, get this value, and I will write this value to R1. That's called, guys, indexed addressing. You are providing the data memory address within a register. That's called indexed addressing. Whenever we are trying to write from the memory or write to the memory or read from the memory, we'll be using indexed addressing. So guys, I repeat, to write directly something into these registers, not the memory, to these registers, directly a value, immediate addressing. You want to exchange information between these registers, direct addressing. You want to read from or write to the data memory to the registers. Then it's called indexed addressing. While we take a deep breath, stop here and get your questions. This was the first complicated thing you've learned. Please.
Hocam, ben bunu pek anladım mı diye sormak istiyorum ama izniniz olursa.
Please.
Hocam direct adreste o zaman direkt gidip adresin içerisindeki bilgiyi alıyor. Mesela M harfini girdiysek birinci adresimize M harfini alıp yazıyor.
Exactly.
Ama indeks adresinde dersek de içindeki bit sayılarını mı yazıyor?
Well, let's first consider the direct addressing mode, and let's not consider something theoretical like N, because you have way to go there. Can you see my whole
Yes.
Okay, can you see? Okay, these are the registers, guys. So this is R0, this is R1, this is R2. These are all 32-bit wide, okay? Which means I have 32-bit values. I'm going to represent these 32-bit values in hexadecimals. So if it is hexadecimal, I have 8 nibbles. So it's like 00000000A. This is a 32-bit value. In this R0, I have this value, guys. So I'm writing a code like this, LDR, R1, R0, which means get the value inside R0 and write it to R1. And since I don't have the square brackets here, like this, I don't have it. So this is direct addressing. Get the value inside R0 and write it to R1, which means after this operation is complete, you'll have the same value in R1. Direct. This is direct. Any questions about direct? I guess not.
Yok hocam.
Okay, then I'm introducing the date. These are the this is a small number of registers, as you can see in the figure. And there is the data memory as well. Data memory, wow. And it is another memory. Yani başka bir renk olarak çıkartıp gene mavi almam gerçekten fantastik oldu. Okay, data memory. Data memory is very large, guys. I mean, in registers, you have just a handful of registers, like 10 or 20, whatever. In this architecture, you have 13 from R0 to R12. You have 13 scratch registers. Data memory is huge. You have many numbers. So these are the same. They are cells. I'll always represent these as these bank notation. This is called bank because if you put something, it's in English, it's called banks. And each bank actually has an address value. So, and each address is 32 bits. For example, this is called 10000000. This is 10000001. The next address, 1000000002. This is. So each address has a value. You can see the screen, right? Each has a value. Good. Imagine I'm going to do another example. In R0, I have this number written. 10000002. And I'm going to write another value here. I'm going to write a value here, for example. 000FFFF. Okay. So this is a memory. Inside the memory, I have this value. The address of this value is this. Actually, çok kötü yazdık gene ya. Bir daha yazayım adresleri de. İnsan gibi. Okay. 10000002. Okay. It's 10, so it's the same. It's the same. I'm going to write another line of code, guys. This time I have the square brackets, right? Which means I'm going to write something over R1. This value will be lost. Where to read it from? Because this is LDR. I'm writing to the registers, loading the registers. Well, we have square brackets. I'm going to read it from the memory. Which address in the memory? This guy will tell me. Because you cannot write the value inside. It should be a register value. In R0, there's an address written. This address, which is it? 10000002. Oh, this is this address. I have this value inside it. So when this code is executed, this will be overwritten. And I will have this value inside here. This is called indexed addressing, and it is the only way you read and write to and from the memory. Screen sharing. Any questions? I guess it's okay. I mean, this is a bit shocking, but when you understand it, I mean, it doesn't make sense. I understand. And why are we doing such a thing? Because arithmetic logic unit is designed such that it can do operations on the registers very fast. However, accessing a huge memory, it's not fast. So the guy is trying to push you to a language, which is called the assembly language, in which you do your operations in the registers and you access the memory whenever you need to. Because accessing the memory, there are two steps. You first access the address here, then you access it. There are 2 steps. So it is like trying to optimize the operation speed using scratch paper, müsvedde kağıdı kullanmak. It is like you are using scratch paper to do your operations. Then when you're finished, you're writing the operations. Okay. Okay, I think we've got it. So we have an idea about the addressing modes. So guys, I'm going to show another example to you, which is called move. Guys, move and LDR, same thing. You are writing something to the registers. But move is a bit limited. You can't do any indexed addressing here. So in LDR R1, so there's no such thing like this. Move with index addressing. No, not allowed. But there is this. You have move R1, for example, A. You are writing the immediate value to A. Well, the natural question, just like there's an example here. Sorry. Here's an example. Or direct, reading from another register. Why? I mean, the best question is we have LDR. Why do we have move? Guys, because move is only 8 bits. Well, this is a bit confusing. Because, for example, I've got move R2 to R1, which means I'm going to get the values inside R2 and write it to R1. But move is 8 bits. 8 bits is how many nibbles? 2 nibbles. Well, I've got 2 nibbles here. So if I write it, what will happen? For example, let's in this configuration, let's do something like this. I'll start with LDR. R0, R1, which means read the value inside R1 and write it to R0. You cannot see it. You see it whole screen, right? If you can tell me. So I'm writing this value over here. Okay, because LDR was a 32-bit operation. Reads 32-bit value from memory to register, register to memory, or register to register. However, move is 8 bits, which means since LDR is 32 bits, these are the entire is 32 bits, I'm getting it all and overwriting it. Okay, if this operation was executed, I would have deleted this one, put all 000 FF. However, if this is move, it is only doing the operation in the least significant 8-bit. The least significant 8-bit, because 8-bit is 2 nibbles, guys. 8-bit, each nibble is 4 bits. 8-bit, 2 nibble. So if I do this operation, it is going to write FF, but it's not going to write these ones, and by default, it's going to write 0, 0, 0. So move is like 8-bit version of LDR. Why do I have it? Because, guys, move is very fast. It is faster than LDR. And sometimes you have to do some small code calculations like a for loop. In a for loop, you have a small variable. You use move. It is faster than LDR. In assembly, you can optimize your code in various ways. And actually, this is one way of doing it. A very experienced assembly coder will know when to use LDR and when to use move. Because move is faster than LDR, guys. Okay? Good. Any questions? This is a limited but faster version of LDR. No questions. You can hear me, right? Okay, I'm sharing the screen again. Ya bu arada bir soruyorum ya, yani bilmiyorum onunla empati kurabiliyor musunuz? Şimdi hiç ses gelmiyor ya, zaten çok şizofren bir şey. Arada bir böyle insanlar yanlışlıkla mikrofonunu açıp hönkürüyordu falan. Rahatsız oluyordum ben. O büyük nimetmiş ya. Birisi falan bir ses geliyor, oh falan içim rahatlıyor. O yüzden hönkürmek isteyen varsa hönkürsün orada arkadaşlar. Okey, şimdi evet mesela ne kadar güzel hönkürmeden. Buyur.
Söyleyecektim ben.
Sor.
Şimdi şu LD'yi anlatırken dedik
Hı-hı.
ki mesela data memory'den register'ın değerini alıyor diye.
Evet.
Data memory'de her register'ın değeri var mı, yoksa biz bir register değeri atıyoruz, ondan sonra mı data memory'de bir değeri oluyor?
Well, I couldn't understand the question actually, but are you asking because you are asking, does the data memory has all register values? Because register is something and data memory is another thing. They are separate. So can you repeat the question in
Hocam
Turkish?
şeyi sormuştum. Mesela R2'ye dedik ya, data memory'den değerini alıp yazıyor işte
Okay,
falan.
I understand. how do we know that R2 has a valid address value, you are asking? How do we know that?
Evet.
Yeah.
Zaten öyle.
Because we define it that way. We define in the code, we are going to write a specific memory address. We are going to write codes in such ways. We will know in which memory location, what we have in which memory location. We are going to write it accordingly. I mean, very good question. One of the most difficult things in this course is to make sense of things. Okay, I understand the mechanism you are saying. I understand it. But how come there's a value in R2 which is an address value in data memory? I'm asking you to bear with me. It will make sense when we write complex codes. I see that you understand the mechanism correctly. Bear with me, okay? It will make sense, okay?
Tamam hocam. Teşekkür
Okay.
ederim.
But it's very, I mean, it's a very legal question. I mean, I understand you. Because at start, it doesn't make sense. Who put those values there? You are going to put them there. You don't know how to put it yet, but you are going to learn. Okay? But know that this is the mechanism. There's no other mechanism. The nice thing about microprocessors is there is no ambiguity. Everything is strict. But there are many rules, but if you learn the rules, it's strict. It's there. Okay? Thank you. Good question. Okay, LDR. Move and STR. The opposite direction for LDR. So you are writing to the memory or to the registers from another register, whatever it is. So you store the values into another register. So it was like in this in LDR we were writing to the registers, right? From by providing a value like this, or from another register, or from the memory. If you want to write to the memory, it is STR. So STR is only used.
Hocam,
Please.
LDR neydi? Tekrar söyler misiniz az önceki cümlenizi?
LDR is the instruction you use to write to a register. Okay, you want to write a value to a register, you use LDR.
Ha, tamam. Tamam.
Hocam bir de Move'da acaba birkaç şey atlamış olabilir miyiz?
Ne gibi?
Slide'da, yani siz sizin önceki yüklediğiniz slide'da 4 tane madde vardı da biz az önce bir tanesini gördük gibi geldi, o yüzden dedim. Şu incorrect kısmı yoktu gibi, o yüzden dedim.
Well, let's go over it. Well, this is an immediate value. You can write this value. This is 256. This is not allowed. Why? Because this is an 8-bit operation. And 8-bit numbers starts from 0 and ends at 255. 256 can only be represented in binary using 9 bits. That's why you cannot do this. It's saying could everybody get it? So let me just put it. Let's finish the lecture with this one. Let's not start STR. This is a good example. Let me just share my screen, share my board. Okay, guys, what happens? Does anybody have any idea? It is move R0 256.
Hocam şu an yazdığınız yer gözüküyor.
Okay, sorry. Thank you. What happens? What happens? So it's either the hash or equals, doesn't matter. So actually, guys, everything happens in binary, but I provided a decimal value. The microprocessor will first transform this value to decimals or hexadecimals. Let's transform it. It is 256. I'll do it quickly for you. 256 in hexadecimals is this, actually. What does this operation do? It gets these 2 bits, right? So in R0, I'm going to put 0, 0. Ignore these values and write zeros. So actually, when I say this instruction, R0 will be 0. That's how it works, guys. Any questions? That's why it's not allowed. You weren't able to load 256. With this operation, you loaded 0 to it. Because it's out of range. Any question? Okay, no questions. And some registers are called classified, guys. Question? Okay, no question. So let me get to some registers are called low registers and high registers. Actually, these first 3 registers are special. They are classified as, let me just share my screen, I'm sorry. Share my screen. These first 3 registers, R0 to R3, are called low registers. They are the special registers. They are so close to the hardware. And actually move can only work with those 4 registers. You cannot move values to R8. This is a specific rule. You don't have to know this because you're not going to use move. That's the rule of it. So will I memorize these rules? And most of the time you read the datasheet. You don't have to. But in time, as you get used to writing with assembly, you'll have to memorize many things. Okay? Okay, I think that's it for today. Let me just